Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on evaluating special functions. And in the last lecture, we discussed how to calculate the Bessel function of the first kind, j nu of x, where nu is the parameter of the Bessel function and x is the variable, which can be real, real, or complex number. And we said that we start with the evaluating the Bessel function for small arguments, and it turned out we can go up to 30, and for that we introduced this power series. All right, and we said that instead of mindlessly calculate each term and then add them up, we reorganize the series into this very clever way, and then we end up with a lead term that we need to only calculate once, and then the rest only depend on the fact that x over 2 squared is common between all terms, so we calculate only once, and then we end up with some terms that have the format of 1 over k times k plus nu, and then we have to calculate them each time. So it reduced the complexity of calculating a j nu for a small x numbers to mainly calculating this lead term, because this lead term involves the calculation of another special function, which is the gamma function, and then a function which is power to some arbitrary number, which is a real number. So these two are the most costly operations in this calculation. All right. Now, before I continue with our discussion on the Bessel functions, I want to jump ahead and discuss the gamma function first, because I told you I used the gamma function, but I didn't tell you how to evaluate it. So I'm going to jump here to gamma function. So basically, gamma function is a function that is designed to generalize the concept of factorial. And if you are not familiar with factorial is basically you take a positive integer number and multiply it by previous integer numbers until you get to 1. For example, let's see, for example, 4 factorial is just 4 times 3 times 2 times 1, which is 24, right? One of the main properties of factorial is that it's a very powerful growth. So as soon as you go to 10 factorial, 20 factorial, it just blows up, right? And then gamma function for any integer n, and it's positive. For any positive integer, gamma of n is n minus 1 factorial. So gamma of 1 is 0 factorial, and by definition 0 factorial is 1. Gamma of 2 is 2 minus 1 factorial, which is 1 factorial, which is 1, right? So gamma of 1 is 1, gamma 2 is also 1. And gamma 3 is 2 factorial, and gamma 4 is 3 factorial, which is 6, and etc. And then for non-integer and complex numbers, we define the gamma function with properties, with 2 properties instead of an explicit equation. And that's why gamma function is a special function, because we don't have an elementary representation of the gamma function, right? So we define it with a property. Just like Bessel functions, we didn't have an elementary representation, but those were the functions that satisfy the Bessel differential equation, right? So here we don't have an elementary representation, so we define it with 2 properties. One is gamma function is the function for which gamma of 1 is 1, right? And then gamma of z plus 1 is z times gamma of z. Any function, we can actually prove this, that any function that exhibits these 2 properties is in fact the gamma function. It's a unique function. So if I have 2 functions for which these 2 properties are true, then the 2 functions are actually the same function, which is the gamma function. All right. Now, similar to Bessel functions, we can have different representations of gamma function that satisfy these 2 properties. The first one is the integral form, as we expect. And the integral form is gamma of z is from 0 to infinity x to the z minus 1 e to the negative z e to the negative x dx. So just note that z is the variable, x is the parameter of the integration, right? So when you calculate this integral, it only depends on z. And the very first thing that you can notice is that for the convergence, we have to have real of z positive. So this integral form is a valid form for gamma only for complex numbers for which the real part of z is positive. Or if z is a real number, then only is valid for positive real numbers. All right. So this integral has a relatively fast convergence for a small z, as we expect. We can choose, obviously we cannot sum from 0 to infinity, so we can choose 0 to 100 as the integration interval. So here's the code. We can have a method gamma, which returns a real number. So the assumption here is that we are evaluating for a real number, double x. So this x is basically this z here. And then I can have an integral function, which is my integrand, func gamma t. T is basically the x, the parameter of integration. T goes to the power t to the x minus 1, e to the negative t. And then integral object, we set the integration function to this func. And again, note that each time we are evaluating at x, we need to redefine our integrand, because our integrand depends on z or depends on x, right? When you change the x, the function that you're integrating over is also changing. And then we take the integral from 0 to 100 with some number of subintervals like 100, 200, 300, and with one of the integration methods that we have looked in the previous lectures. Here I'm just assuming it's Simpson. All right. But again, integration is not the most efficient way of calculating, so we want to use power series always for evaluating special functions that don't have an elementary representation. So this is the Euler's definition. Euler was the first one to propose this power series for the gamma function, and this is not a summation. Typically when we say series, it's a summation of some terms, but here is actually a multiplication, and naturally we expect the multiplication to happen, because even if you look at the integer numbers, it's some sort of multiplication of some numbers, right? So it's very natural to see to accept the fact that gamma function is a multiplication of some numbers, right? So this goes from 1 to infinity. So what we do, we create a sequence that calculates from 1 to some number of terms, let's say n. And then we accelerate it with Richardson, because unfortunately this sequence has a painfully slow convergence. So we have to accelerate it, and Richardson acceleration is the appropriate one, is the most suited one, because again, Richardson is good when you have a monotonically increasing or decreasing behavior. And obviously this is just monotonically increasing, assuming that z is positive, real, because n is positive, right? So I'm creating a gamma sequence. N goes to power 1 plus 1 over n to the power of x, right? So this is the numerator, divided by 1 plus x over n. This is denominator. So I define a sequence that calculates the term, and then I define another sequence that calculates the products. So n goes to, I start from 1, I from 1 to n, I plus plus, result, gamma sec, evaluate at I. I didn't really need to define this sequence. I could just put this on the right hand side here, right? So we can do that. So this sequence returns the product of these terms from 1 to n, and then we Richardson it. Note that there is 1 over z that doesn't depend on n or the number of multiplications. So we evaluate this at the end. So the limit, if we take the limit, we have to first find the value of this sequence. So sequence product, Richardson fourth order, accelerated, evaluated at some number, let's say 300. We will look at the convergence to see whether or not 300 is a good number for evaluation. And then finally we divide it by x or z here, all right? And again, we're going to also basically compare the speed of these two, but by now you should already know that integration is a very inefficient way of calculating. So if we calculate for 1000 different x values, this integration is going to take much more time than just this multiplication, all right? All right, so this product series gives us a very important property. First of all, unlike the integral definition that is only valid for complex numbers that have a positive real value, this product series this product definition is valid for any z, because 1 over z obviously is valid when z is not 0, because there is no operation here that we cannot define for a complex number. Everything is defined, right? We know what is 1 over z, we know how to take a number and raise it to some power, and we know what plus z over n is, and we know how to divide by this. So this definition is valid for all complex numbers without any condition, and that's very good. But then what we see here is that if z is a negative integer, if z is 0 or is a negative integer, we have singularities. This blows up, right? Because we are dividing by 0. And we cannot get away from it, because even if we take the limit as z reaches a negative integer, this always blows up. So the limit is actually infinity. And that's true. That's definitely true. That's one of the properties of the gamma function, is that the gamma function blows up at negative integers and zeros. So this is a plot. I'm plotting from minus 2.999 something all the way to 1. And as you can see, at 0, minus 1, and minus 2, we blow up. All right? And we can go ahead and do a comparison with Python, the similar thing that we did for Bessel functions too. But before doing that, these are the plots of the comparison. As you can see, this implementation is good, and this is the right definition of gamma function in terms of numerical efficiency. All right, but there is one thing that we can do better, and that's how we are evaluating this. All right, so in Euler's definition, we take 1 plus 1 over n to the power of z and multiply them. So we have to take power and multiply them n times, and n goes to infinity, right? But again, because gamma function was defined based on a property, not an actual elementary definition, we can have also other definitions. So the other one is Weierstrass. Weierstrass definition tells us gamma z is e to the minus gamma z, this little gamma, which is called Euler constant or Euler Mascheroni constant, divided by z, and again another product from 1 to infinity, e to the z over n, 1 plus z over n. So this term 1 plus z over n is similar, 1 over z is similar, but now we have these exponentials, all right? And you can verify that both of these definitions satisfy these two properties. So any definition that satisfies these two properties is a valid representation of gamma function. We can prove that. Now this Euler Mascheroni constant is just a number that you can just Google it. Here I'm writing it up to 6 decimal places, which is a pretty good accuracy. And then the question is, okay, we have these two definitions. Both of them are based on some products, right? And basically they are both based on elementary functions. Here we have power, some number to some power, and here we have exponentials, right? So the question is, which one should we use? Which one can give us a faster or more efficient way of calculation? And the answer is Weierstrass appears to have a slight edge here, so it's slightly better. And both of these again work for complex numbers without any restriction on z, because again we know how to define exponentiation for any complex number. And before continuing, I want to also mention there is one very interesting property of the gamma function, which is for non-integer z, non-integer values of z. This is called a reflection formula, or Euler's reflection formula, and that's very interesting. If you take gamma z and multiply it by gamma 1 minus z, it's like we take a number and reflect it about the 1, z equals 1 axis, the vertical axis. Gamma z times gamma 1 minus z, it actually has a definite value. So This gamma doesn't have a elementary representation, but gamma z times gamma 1 minus z turns out to have an elementary representation, which is pi over sine of pi times z. And again, it doesn't matter if z is a real number or complex, because we can define the sign for both real numbers and complex numbers. Now the interesting case is when z is equal to 1 over 2, then 1 minus z is equal z, right? So gamma 1 over 2 squared is pi over sine of pi over 2, which is 1. So gamma of 1 over 2 squared is pi. So gamma of 1 over 2 has a definite value, a square root of pi. That's a very famous number, gamma of 1 over 2. Alright, so let's look at how I implemented this Weierstrass definition. So the previous slide was the implementation of the Euler definition. Now I'm calculating the implementation of the Weierstrass. So gamma sec product, n goes to from 1, so we are multiplying 1 plus z over n, so we are calculating the denominator, and then the sequence sum. What is the sequence? So I can bring this exponential inside, and when we multiply exponentials, we can just sum up all the powers, all the exponents, and then calculate the exponent first, and then take the exponential function for that evaluated exponent. So I'm multiplying all the exponentials and summing all over the exponents first. So 1 over I, so we have 1 over n here, and we sum them up, and eventually we reduce this Euler number, and then the total sequence becomes exponent of x, which is z, times whatever we calculated for this sum of powers, evaluate and the nth term, and divide by the denominator, which is gamma sec prod evaluate at n. All right, so this product sequence evaluates the denominator, this sum evaluates the exponent of this exponential function after multiplication n times, and then we have the sequence total, which is just evaluates the sequence after n terms. And eventually we recharge on it and then evaluate it at some number of terms, let's say 300, and then divide it by this z. All right, so these two definitions have some common terms, right? 1 over z is the same, 1 plus z over n is also the same. The only difference is here we are summing up some numbers and then invoking the exponential function on it. Here we are calculating the number, raising it to some power, and then multiplying them. So it's kind of obvious why Weierstrass is better, because we do the power raising to some power and then multiplying, so we are calling the power function many times, and that's inefficient in terms of calling the exponential function once. But we can actually improve the implementation of the Euler's definition, because I know that if all the powers here z are the same, and then I can multiply the bases first, so 1 plus 1 over n, I multiply them, evaluate it after some n terms, and then raise the result to the power of z. All right, so calculate this base first, which is a multiplication, and then raise it to the power of z, and then divide it by 1 over z times the other term. Now compare it to the Weierstrass. In Weierstrass, 1 over z and this denominator are the same. However, here in the numerator, we sum the terms 1 to infinity 1 over n, all right, and then minus gamma, and then times z, and then take the exponential. So now in this definition of the Euler, in this implementation, we are invoking the power, this power function, only once after calculating all this multiplication. All right, so what I would like you to understand is that the most efficient way of calculating these products is such that we reduce the number of times we invoke these elementary functions like exponential or power. The most efficient way is just to have a bunch of numbers and multiply them, add them together, and divide them by each other, right? This is the easiest thing for a CPU to do, right? It doesn't take much time. And between all these four elementary operations, addition, subtraction, multiplication, and division, I think it's obvious that addition and subtraction are the fastest. Addition is the fastest, and then subtraction, and then multiplication. And the slowest one is always the division, right? For a CPU to divide two numbers, it has to work more than multiplying two numbers or adding two numbers. So you want to keep the divisions to the minimum and have more multiplication or addition, right? So if we compare these term by term, we see that the only difference is in the numerator, right? The denominators are the same. And here, if we are evaluating for n terms, we have n division and then n addition, which is 2n, and one subtraction, which doesn't matter, and then one multiplication doesn't matter. So 2n until we get to this exponential thing, right? Here, each term has two operations, 1 plus 1 division. So two operations, we have n terms, 2n, and we have to multiply them, 3n operations. So eventually it boils down to the fact that Weierstrass has always a slightly better edge in terms of efficiency, because if I'm evaluating at 300 terms, this Weierstrass requires 300 less operations, even though those operations are simple division and multiplication of some numbers. All right. So Weierstrass turns out to be the fastest. And here's again, I modified this implementation of the gamma based on Euler's. So instead of invoking the power function on each term in the numerator, here I'm calculating the numerator first, which is 1 plus 1 over n. I'm calculating this product first, and then invoking the power on this product and raising it to the power of x. And then divided on the product of the denominator, and eventually this is our sequence which converges, and when it converges we divide it by x or z. All right, just note that it's very interesting, the sum of 1 to infinity of 1 over n doesn't converge, it diverges. But when you calculate it as part of the whole sequence here, this product sequence, the product sequence actually converges, because the denominator diverges, the numerator diverges, infinite over infinite turns out to be a non-infinite number. All right, so let's head to Eclipse and try to look at the implementations and compare the power, compare the speed. So here's my Eclipse. I have this gamma function, and in this gamma function, obviously the first implementation is just the naive integration, which right out of the gate doesn't work for negative numbers. So this is the integration implementation, t to the x minus 1, x power of negative t, and we're integrating with Simpson from 0 to 100, and the order is 1000. I mean, you will see that if we reduce the order, it's not going to give us a good accuracy. So we have to have a very large number of subintervals, okay? So gamma 2 is the original implementation of the Euler. So this is the original implementation of Euler's definition of gamma function. All right. So here we are calculating the power. So basically by original definition, I mean this one. 1 plus 1n raised to the power of x or z. That's what we're doing. And divided by 1 plus x over n. And again, this means we are evaluating each term of this product first and then multiplying them together. So this product is just evaluates the terms and multiply them, and then we accelerate the sequence, evaluate it at 300 and divide it by x. All right. Gamma 2 modified is basically the enhanced version of Euler's definition. So by enhanced, what do I mean? I mean that we are multiplying 1 plus 1 over I. First we calculate the multiplication or create a sequence that calculates the multiplication for n terms, and then we raise it to the power of x, right? And then in the gamma sec product, here we are calculating 1 over 1 plus xi, 1 over 1 plus x over I. So basically here I'm assuming that this becomes this sequence raised to z times 1 over, or basically the product of 1 over 1 plus z over n, right? And then eventually the denominator is multiplied by this power, because this is actually 1 over denominator. Gamma 3 is Weierstrass definition. So this is Weierstrass, how do we write it? Weierstrass's definition, implementation. Okay, so we are calculating 1 plus x over I and calculating the product, which is this one, the denominator, and then we are doing the summation in the exponent, 1 over I from 1 to n, and then reducing this g, which is the Euler's number. All right. And then once we do these, and these are, as you can see, these two sequences are just elementary operations: division, multiplication, summation. What I want to point out is this one, 1 over I. You have to be very careful about this type of operations, because if you just write 1 over I, the compiler will see it as integer divided by integer, and because I is greater than 1, it returns 0. So you have to always be cautious that you have to convert this to double. Either 1.0 or 1D or 1F. Float works fine too. So here I'm converting the 1 to double. So I want compiler to always calculate and return the exact double value, right? So if you define it as 1 over I, this hints to the compiler that this is an integer if you don't add this 0.0, right? And then compiler says, okay, the user is defining integer divided by integer, and I is greater than 1, so it returns 0, which is incorrect. All right. So let's write not correct. So be careful when you do this kind of divisions involving I. Here x is double, so compiler already understands whether or not I is integer is irrelevant, because the integer is promoted to double first and then the division is performed. That's one of the promotion rules in the elementary operations in Java. When you have two numbers, the types are different. The type that has a smaller type, the number that has a smaller type is promoted to the larger one. i.e., compiler always performs implicit casting. But whenever there is an explicit casting required, the compiler will give an error and forces you to fix it. All right. And so if I have an integer and double, the integer is promoted to double. So basically the compiler does this. Double, basically this. The compiler actually does this. So it converts I to double first and then does the division. But here, if I write 1 over I, the compiler assumes that this is integer over integer. I have to hint the compiler because the types are the same. So without any hint to the compiler just assumes integer over integer. So I can do this, for example. So here 1 is converted to double first. And I can do this, 1D or 1D. Or I can convert the I to double first. But the easiest thing that is always nice to do is add a decimal place for the double numbers. All right. So this is the most efficient way of implementing Weierstrass. Gamma 4 is the most efficient implementation of Euler's definition. And by that, I mean, I'm not doing here I'm calculating 1 over 1 plus x over I and then multiply the result by this power. Here I am calculating 1 plus x over I, which is the denominator, and then dividing the power by that. All right. So gamma 3 and gamma 4 are supposed to be the most efficient implementations based on Weierstrass and Euler. So let's go and test them. I already have created a test class here. It has the main method. I create this gamma function object. and I create my timer, and I have one figure to plot them. All right, so let's say I want to plot from almost -1, which we do have a singularity at -1 and 0, up to 5 for 1000 x values. So, and we already know that our first thing was the gamma. This is based on integration. This is going to be painfully slow. Let's run it. It takes 261, and obviously it blows up when we end up with we have negative numbers, or we approach 0, right? The first singularity of the gamma function is at 0. So let's try to evaluate from 1 to 5. 1 double to 5. It takes 269, and at 1 we get a little bit of, at 1 we get 1, and at 2 we should also get 1, because 1 factorial, at 1, gamma of 1 is 0 factorial, which is 1. Gamma of 2 is 1 factorial, which is also 1. All right, let me just increase the font. Gamma of 3 is 2 factorial, which is 2. All right, gamma of 4 is 3 factorial, which is 6. Okay, and gamma of 5 is 4 factorial, which is 120, which is 4 factorial is 24. So the accuracy is good. So we're using Simpson's method for integration. We are dividing 0 to 100. I mean, our infinity, we're assuming 100 is good, and that's good. And 1000 subintervals. But the time it takes is about 270 milliseconds. All right, so the next one, let's try gamma 2. And okay, so let's try gamma 2. So gamma 2 is based on the Euler's definition. Euler, I'm going to call it naive implementation. The naive implementation is just calculating this each term first. So we call this power function each time. We calculate one term, do the division, and then multiply the results. This is the naive implementation. So from 269, we are going to 156. So a factor of 2, all right? And the accuracy is still good. 5 factorial is 24, 4 factorial is 6. All right, so a factor of 2 reduction. Gamma 4 is the most efficient implementation of Euler definition. So Euler, but this is most efficient. All right, so I'm not going to look at gamma to modify, because there is no need to do that. So from naive to most efficient. So keep this 156 in mind. Let's see what happens. We go to 40. Now we're talking. It's a factor of 4 reduction. And remember what we did. The naive implementation is do the power 1 plus 1n to the power of z first for each term, and then multiply them. And we already know that calling the power function is very costly. It's one of the costly things in this calculation. So in the most efficient way, what we are doing, we are multiplying 1 plus 1 over n first. And again, because all these terms in the numerator share the same power. So we multiply the bases first, and then call the power function one time to evaluate the whole thing. All right? And it was a factor of 4 reduction from 160 to 40 milliseconds. All right? Now, obviously, the last one, gamma 3, is the Weierstrass. Again, how do we write it? Weierstrass. And the most efficient. So 40 milliseconds for Euler, 40 milliseconds for Weierstrass. So there is not much edge here, right? We are calculating 1000 values, right? Now, as I said, the difference between Weierstrass and Euler is a fact. If we are evaluating n terms for this product, is so Euler numerator requires 3n, Weierstrass requires 2n. when n grows, let's say instead of 1000 terms we calculate 5000, right? So what happens if I try to calculate 5000 times? So Weierstrass gives me 130, Euler gives me 133 milliseconds. So Weierstrass implementation that we did has a slight edge, all right? And unlike the integration, the Weierstrass also works for any number. So let's say go from minus 0.99 to 5,000 terms, or just 1000 terms, all right? 42 milliseconds, and we see this singularity here. If I continue to -1, we have another singularity, all right? So let's start from something close to 0.1. All right, this looks fine, all right? And let's, just like we did for Bessel functions, let's export this to Python and try to compare the values with what we get from the Python implementation. So I'm going to export to a text file, all right? And then on my desktop, I'm going to open with a text file. These are all just the values, and copy them. And then I'm going to my my Jupyter notebook. So I already have NumPy imported as an NP, matplotlib, PLT. I'm changing the font size of the plot to 15 and also increasing the size of the figure. And gamma function, just like Bessel functions, is in the special package of SciPy, all right? So let's bring our copied values here and then plot them. PLT, plot x0, y0, and then color B, and label it Java. All right, this is our Java, and let's make sure we turn the legend on. So this is our Java, and we want to calculate from the SciPy and do a comparison. So let's x0 SciPy special, and we want to calculate the gamma function. And this gamma function takes iterates over arrays, so I can pass in a list and color red, and let's call this Python. And maybe let's also give it a line style dash. As you can see, it pretty much matches what we are calculating in Java. And again, our implementation in Java is the most efficient implementation. This Gamma 3 Weierstrass. All right. I hope you enjoyed this lecture. I will continue our discussion on the other Bessel functions in the next lecture. Thank you, and I'll see you in the next one.